Mhm. All right. Good morning or good afternoon, everyone. It's my great pleasure to introduce Professor Ulla Svensson. Ulla is an associate professor in the School of Computer and Communication Sciences at EPFL. He works in approximation algorithms, combinatorial optimization, computational complexity, and scheduling. He has won several prestigious awards, including National Academy of Sciences Health Prize and several Best Paper Awards. In the next 45 minutes or so, he will tell us about polyhedral techniques in combinatorial optimization, matchings, and tours. Take it away.
Thank you very much. Yes, so my name is Ulla Svensson. It's a great pleasure to be speaking at ICM. I will talk about polyhedral techniques in combinatorial optimizations, combinatorial optimization, matchings, and tours. So it's not a new topic to address polyhedral techniques in combinatorial optimization, and there are several beautiful books written about this topic. But today I would like to report on some recent progress on two classical questions in combinatorial optimization. So the first question is the perfect matching problem, which we see as one of the favorite benchmark problems of that is polynomial time computable. So here we have a biptype graph with edge weights. Here's a edge weight 3, 1, 1, 2, 1, and 2. And a perfect matching of maximum weight in this case is the one indicated in red. It has weight 3 plus 2 plus 2 equals 7. So for biptype graphs, we can actually trace back an efficient algorithm already to Jacobi in the 19th century. And for general graphs, groundbreaking work by Edmonds solved it in 1965. So in short, we have decade-old beautiful deterministic algorithms for max weight matchings that find such matchings efficiently. But if we slightly change the question a little bit, it remains a major challenge to find such efficient deterministic algorithm. So instead of finding a perfect matching of maximum weight, could you find a perfect matching whose weight equals a given target? So it's a challenge I will come back to later in the talk. So the second problem we're going to talk about is the traveling salesman problem. This is another classic question in algorithms, and variants were studied by Hamilton and Kirkman already in the 19th century. So to visit the end cities in the shortest possible way is an attractive and simple statement. So it appears in popular contests. Even I saw it appeared as a preschool assignments. And maybe a very important paper for us is that Danzig, Fox, and Johnson, already in 1954, found the optimal tour for visiting 49 cities. So in that paper, they proposed a linear program. And till this date, it remains an open question, a very open question, what's the strength of this technique? So what's the best possible algorithm for this question? So the outline of the talk is that I will start to talk about the algorithms for the matching problems, and then I will come back to the traveling salesman problem. So while these problems are different, kind of a personal satisfaction was that the techniques that were developed for the perfect matching question also then inspired and transferred to our result for the traveling salesman problem. So let's start from the beginning, the perfect matching problem. So here I'm given a graph, and I want to output a matching M of maximum cardinality. So matching is just a set of edges so that each vertex is incident to at most one edge. So here we have indicated a matching in blue, and it's a perfect matching because each vertex is incident to exactly one edge. As I said, this is a special program in computer science, a special problem in computer science that we like to study in many models of computation. For example, monotone circuits, extended formulations, parallel streaming, sublinear, online algorithms, and so on. And what we're going to do is to focus on parallel algorithms for the perfect matching problem. And this allows us to also make a connection to a very beautiful question in computer science, namely, does randomness significantly speed up computation? So how valuable is it to have randomness when we design algorithms? At first sight, it's tempting to say, yes, randomness is really helpful to give fast algorithms because we have many problems for which we only have randomized efficient algorithms. One example is polynomial identity testing. So where to verify whether a polynomial is identical to 0 or not. So for example, the polynomial can be given as the determinant of a couple of variables. So if you want to verify whether this polynomial is identical to 0 or not, there's an easy randomized algorithm. Just replace each variable with a random value and simply calculate the determinant. However, there is no non-trivial deterministic algorithm known for this question. So at first sight, when you see this question, it's probably time to say, yes, randomness is really useful when devising efficient algorithms. But then complexity theory actually tells us that it's probably not the case. One of my favorite theorems in this line of work is by Impagliazzo and Vigdesson, who show that if SAT cannot be solved by circuits of sub-exponential size, then any polynomial time randomized algorithm can be made a deterministic polynomial time algorithm. So in fact, the belief is that all efficient computation can be de-randomized. This is kind of good news if you would like to devise algorithms, because if this is true, there must exist powerful deterministic algorithmic techniques yet to be discovered. And this is the situation if we look at parallel algorithms for the matching problem. So let me now return to that question. Okay. So just as a high-level description, with parallel algorithms, I mean algorithms that run on many processors, polynomially many processors, and really fast in polylogarithmic time. And here, one of the main open questions is whether the matching problem has a parallel polylogarithmic time algorithm. And one of the reasons that we care a lot about this question is that we have had randomized parallel algorithms for the perfect matching problem in over 4 decades. So a little bit more detailed history is that Lovász in 1979 gave a randomized parallel algorithm for deciding whether a given graph has a perfect matching or not. The search version, also outputting a perfect matching, was later resolved by Karp, Uppvall, Vigdesson, and Mulmuli, Vazirani, and Vazirani. So if we believe that we can de-randomize efficient computation, we should be at least able to de-randomize one of these algorithms and give deterministic algorithms for this question. And for the matching problem, this looks like a much easier question than the most general one to de-randomize all algorithms, because we have a lot of knowledge about perfect matchings in a graph. So prior results, there has been a lot of work for special graph classes. I don't expect you to read all the citations here, but you can note that it's all also still remains open even for biptype graphs. That said, there was major progress in a very beautiful paper by Fenner, Gurria, and Tirov in 2015, who almost de-randomized algorithm in the case of biptype graphs. Specifically, they give a parallel algorithm that runs in polylogarithmic time without any randomness, but use slightly too many processors to completely de-randomize. They used m to power polylog n processors instead of polynomially many processors. And our contribution was to use our polyhedral understanding to generalize their results to general graphs. So now in the next couple of slides, I would like to describe the basic approach Fenner, Gurria, and Tirov used for de-randomization, and then the obstacles that we had to face in order to turn their result into apply for general graphs. So basic approach for de-randomization. Well, just take an existing randomized algorithm and de-randomize it on a very high level. So let's look at the randomized algorithms we have for solving the perfect matching problem in parallel. So they're all based on what's called the TAT matrix from 1947. And for the purpose of this talk, everything you need to know about the TAT matrix is that the TAT matrix of a graph is not identical to 0 if and only if G, the graph, has a perfect matching. So once we know that, there is kind of a clear randomized algorithm. Let's just substitute each variable with a random value and calculate the determinant. And Sank in 1976 showed that we can calculate the determinant of a finite field in parallel, over a field can be calculated in parallel. And this is the algorithm by Lovász in 1979. The second randomized algorithm that we're going to describe is by Mulmuli, Vazirani, and Vazirani, and will be more attractive for de-randomization. It almost proceeds exactly as the previous algorithm, namely for each edge, we select a random weight from, let's say, 1 to n squared. But then instead of replacing each variable xc in the TAT matrix by the random weight, we replace it by 2 to the power of the random weight. So because we replace the variable by 2 to the power of the weight, it's important that these weights are polynomially bounded. But I will come back to why this is good for us in just a moment. So notice that the algorithm consists of 2 steps. The first step, where we use randomization, and the second step is completely deterministic. And the nice thing by the algorithm by Mulmule, Vazirani, and Vazirani is that the second deterministic step has a very nice criteria for when it's guaranteed to succeed. Specifically, step 2 is guaranteed to succeed if weight function W that we selected in the first step is isolating. And isolating, a weight function is isolating if the min weight perfect matching with respect to this weight function is unique. And they complemented this result by showing that if we select the weight function at random, then with good probability it is isolating. In other words, if we would like to give a deterministic algorithm for deterministic parallel algorithm for the perfect matching problem, all we would need to do is to construct an isolating weight function in parallel time. So that's a task that we are facing. And in fact, we will do something that, or Fenaguria-TF do something that I find even more nice, and that's what I call oblivious de-randomization. So remember, our challenge here is to, on input the graph G, construct an isolating weight function in parallel. But they do an oblivious de-randomization. So they only take input the size of the graph, and they show how to construct a family, capital W, of weight functions, of nice weight functions that can be computed in parallel, such that for any n-vertex graph, there is an isolating weight function. We also would like that for every edge, the weight of this edge is polynomially bounded. Remember that we replaced the variable xe by 2 to the power of we. And we would like that the number of weight functions are polynomial. If you have such an oblivious de-randomization, we can just run all the weight functions in parallel. And since one of them is guaranteed to be isolating, we are guaranteed to succeed. And notice that we can afford to run all of them in parallel because they're polynomially bounded. Just to get comfortable with this definition, notice that if I drop the second condition, then it's easy because we can use exponential weights on the edges and therefore having isolating weight function. If we drop so we only need one. If we drop the third condition, then we can just look at all the CO1 weight functions and one of them will be isolating. But the best bound we have here is exponential. And I said that this is a difficult task to construct such a family. And what Fenaguria-TF did was to almost succeed. Namely, they got n-to the power of polylog n and n-to the power of polylog n here. That's why they got n-to the power of polylog n processors instead of only polynomially many processors. And what we did was to prove that for general graphs as well. So one of the main insights now we know we would like to construct such a family of weight functions. And one of the main insights by the proof of Fenaguria and TF was kind of counterintuitive maybe to computer scientists, because we like to use greedy. But if you have seen the end of this movie, you might need that we should not be too greedy. Okay. So what they do is instead of showing that there is such a family, let's select the weight functions in steps and slowly but safely become find out isolating weight function. Okay, so let's make progress step by step. Okay, so we let capital or cal W be a set of nice, polynomially many nice weight functions. The exact definition here is not important for this talk. And we have the set of all matchings of G. Now we select a weight function from the family and we let M1 be the subset of perfect matchings that minimize this weight function. Okay, it might not be isolating, and one might contain more than one perfect matching. So we select W2 from the same family, and we let M2 be the subset of M1 be the perfect matchings in M1 that minimize W2, and so on. We continue until we have a set of one perfect matching, meaning that we have isolated a perfect matching. Now the question is, how many weight functions from this nice family is necessary for us to guarantee that there is only one minimizer in ML? And what they proved is that we only need log n weight functions. And notice that this gives the oblivious de-randomization because this allows us to try all possibilities in cal W in parallel. There's nth of log n choices of W1 to W log 2n. So that's why they get nth of log n, a family of nth of log n weight functions. And this is a lexicographic minimization, but you can turn it into a normal minimization by just having a huge weight on the first weight function, a slightly less weight of the second, and so on. So to prove that you only need to select log n weight functions to be guaranteed to be isolating, you need a good progress measure. And one can interpret their method from a polyhedral perspective as follows. Okay, so we have the convex hull of perfect matchings here. So each extreme point is just the indicator vector of a perfect matching. So first we select W1, we minimize it, meaning that we hit the face of this polytope, a subface, which is the convex hull of the perfect matchings that minimize W1. So we have 3 perfect matchings that minimize W1. Then we stick on this face F1 and we select a second weight function and minimize it. Now we have 2 perfect matchings on this face that minimize the weight function W2. And we stick on this face and we select the third weight function. And now we have an isolating weight function. We have a unique optimum that lexicographically minimizes W. And to prove that you only need to select log n of these weight functions, what they use is the very nice structure of the bipartite perfect matching polytope. And you can see that every face, because of its simple description, every face is in fact just a subgraph. You throw away edges. And the key property that they can prove is that the girth, namely the length of the shortest cycle, doubles in every step. So if you double the girth, the length of the shortest cycle for log n steps, then you don't have any cycles in your graph anymore. And the mean weight perfect matching you can prove is unique. Now the obstacle for general graphs is that the description of the perfect matching polytope is kind of much harder, much more complex. So the description for bipartite graphs is just that the degree of each vertex should equal 1 and each edge should take a non-negative value. So here I have a variable xe for every edge, and I have the notation x delta s to just be equal the sum of edges that crosses the cut defined by the subset S of vertices. So this just says that the sum of edges incident to V should equal 1. We should pick exactly 1 edge incident to each vertex. So this is a description of the bipartite perfect matching polytope. And now there's 2 equivalent definition of faces. One is that a face of a polytope is the convex hull of solutions that or extreme points that minimize this weight function. Another one is that it's obtained by setting a subset of the inequalities to equalities. But here, the only inequalities we have are xe's at least 0. So setting them to equality is just throwing away edges from a graph. So every face of the bipartite, in the bipartite case, is just a subgraph. Edmond's description for general graphs from 1965 contains exponentially many more odd cut constraints. It says for every odd set of vertices, at least one edge must cross this cut. And this makes the life much harder to make a good progress measure. In particular, this small graph can be seen to be a counterexample to the girth progress measure. So let me now mention 2 key ideas what we use for general graphs. First is, okay, there were exponentially many of these odd cut constraints, but in the end of the day, they are not too bad. Because consider such a tight set S that is tight in our face. That means that any perfect matching in the current phase where we are should use exactly 1 edge crossing this cut. So once we have selected such an edge, the instance decomposes. Once we have selected such an edge, we cannot take any more edge crossing this cut. So the instance decomposes into 2 independent subinstances. This is kind of our best friend for divide and conquer. Okay, so once you have an odd cut constraint, you know that there should be exactly 1 edge crossing this cut in your perfect matching. So once you fix that edge, there is at most n squared possibilities. You have 2 independent instances. And we combine this very easy high-level idea with our polyhedral understanding of the perfect matching polytope. In particular, any phase, you know, we had exponentially many cut constraints, but any phase is defined by Laminar family of vertex subsets. So a family of sets is laminar if every 2 subsets are either disjoint, like this set is disjoint from this set, for example, or one is a subset of the other. And it's a fact that a laminar family has size at most 2n minus 1. So instead of caring about all these exponentially many constraints, to define a phase, we only have to care about linearly many constraints. And I will come back to this laminar structure of phases or extreme points when we come to the asymmetric TSP. But it's kind of nice that we will see that the very similar techniques apply to that result. So to summarize this high-level description, we had that the dangerous odd set constraints are actually our best friend for divide and conquer. And the laminar structure faces of the polytope allowed us to give a progress measure for general graphs that allowed us to generalize the proof by Fenagoya-Tira for biptype graphs to general graphs. And other results following the technique of Fenagoya-Tira was the randomization of the isolation lemma for matrix intersection, totally unimodular polytopes, and also finding a matching planar graphs in NC. This results here is slightly different in terms of techniques, but follow some of the ideas. I would like to remark that all these, our results for general graphs and these results, they rely on our excellent understanding of the associated polytopes of these problems. And keep that in mind, because now we return to the problem we stated in the beginning, and one other, so I will mention two fascinating open problems related to this. So we have a n by n biptype graph with polynomial edge weights. So the first one was exact matching. Is there perfect matching of weight equal to capital W? And the other one is top K matching. Find a perfect matching that maximizes the sum of weights of the K heaviest edges. So for these two questions, we can solve them with randomization, in fact, in general graphs, by the very versatile algorithm that I described by adapting the algorithm by Mulmulé, Vazirani, and Vazirani from 86. So we can solve them in parallel efficiently, but we don't even have the deterministic parallel sequential algorithms. No, sorry, we don't have the deterministic efficient sequential algorithms for these questions. And a major issue for pushing the techniques that I described on the previous slides is that we do not have a polyhedral understanding for these questions. So I think that's very interesting future directions. Okay. So now that finishes the first part of this talk on the perfect matching problem. Now we'll turn my attention to the symmetric traveling salesman problem, and we'll see the first constant factor approximation algorithm for this question. And we'll see that some of the techniques that I mentioned for the matching problem will also transfer here. Okay, so the traveling salesman problem. So this is the question of finding the shortest tour that visits n given cities. So maybe that's the shortest tour. And if the matching problem is one of our favorite benchmark problems in P, I would say that the traveling salesman problem is one of our favorite NP-hard benchmark problems. So there's several books and so on written about it. And you know, this is a problem that we like to study both from theory, but also more practical solvers have been very good at that. So now you can solve huge instance. For example, you can calculate what is the shortest way to visit all the pubs in the UK. It turns out to be this one, calculated by Cook et al. In 45 million meters. So we will look at this, of course, from a more theoretical perspective. So there's two basic versions. That is that the distance, it's a symmetric case where the distance from city U to V equals the distance from V to U. And there's the more general asymmetric version where no such assumption is made. So distance from U to V can be 100 and the V to U can be 3. So in the asymmetric TSP, we're given as input an edge-weighted digraph. G, we assume it's strongly connected. And we want to find a tour of minimum weight that visits each vertex at least once. So here's distance 1, distance 3, distance 1, 5,000. It's asymmetric. Here's a tour. And notice that I'm allowing you to visit a city more than once, but we should visit each vertex at least once. This is equivalent of finding a Hamiltonian cycle if we assume the triangular inequality of the distances. And this is a necessary assumption to get any theoretical guarantees on the approximation guarantee. So I like this version where we visit each city at least once. And a more graph theoretic formulation of this question, a tour, would be to find a connected Eulerian multiset of edges. Okay, so a multiset of edges. I'm allowing you to use an edge more than once. You want to connect the graph, and it should be Eulerian, meaning that the in degree is equal to out degree. You can see that, you know, clearly a tour has, you know, in degree 2 if you visit and you're out degree 2. So in degree should equal the out degree. And this turns out to be sufficient conditions that it should connect the graph, the edge set that you select, and it should be Eulerian. So that viewpoint naturally leads us to the standard relaxation, where we have a variable xuv equal the number of times we traverse edge uv. We want to minimize the total weight we spend. So the weight of an edge times the number of times we traverse it. We want that the out degree should equal the in degree, so the Eulerian condition for every vertex. And we also want to avoid subtours. So we said that for every subset of vertices, we should have at least 2 edges crossing the cut. So at least once we enter and one we go out. And here I use the notation for set S. Delta plus S is the set of outgoing edges. Delta minus S is the set of incoming edges. So this notation is just that the sum of edges going out of V should equal the sum of X value of edges coming into V. And I use delta S to be the union of the two. So this just says that the cut where I take both in and outgoing edges should be at least of size 2. So now a long-standing question here is, what is the strength of this standard LP? And this is puzzled researchers for decades, and we believe it's conjectured to be a small constant. For a symmetric case, it's 2, and for symmetric, we conjecture it to be 4/3. And to answer this question, I will focus on asymmetric now. There's mainly been 2 approaches. And remember that the conditions of a TOR was that it should be Eulerian and it should be connected. But if you drop one of these conditions, the problem becomes easy. So in fact, it's easy to find an Eulerian graph. We can find something called a mean cost cycle cover, meaning that each vertex is part of exactly one cycle. And it's easy to find a connected graph that's just a mean cost spanning tree. So this is 2 approaches. Either we drop connectivity, we find Eulerian graphs, and we build up connectivity here, repeatedly, bottom up, or we find a minimum spanning tree that ensures connectivity, and then we patch up Eulerianicity later on. Okay, so the first approach that leads us to algorithm by Friis, Galbiati, and Maffioli from '82. That finds a mean cost cycle cover. A TOR is a special cycle cover of one single cycle. So the cost of this mean cost cycle cover is at most opt. Select a representative in each component. Find a mean cost cycle cover, of course, at most opt. Select a representative in each component. Find a mean cost cycle cover of a cost of most opt. Until you have connected the graph is connected, every vertex is Eulerian, so you're happy. So here in this case, the total cost will be at most 3 times opt. And in general, the total cost will be at most the number of iterations you do, which is at most log base 2n, because every cycle cover you do at least halves the number of components. Okay, and the worst case is that all the cycles would have length 2 all the time, so you would only halve the number of components, and you would need log base 2n iterations to connect your graph. Okay, so that gives us the log 2n approximation by Friis, Galbiati, Maffioli. So you may say, oh, this is very pessimistic. Why should you only find cycles of length 2? So I agree, but this turns out to be hard to prove. So it took to 2003 Bless who got a 0.99 log base 2n approximation. And the world record in pushing this is still a 2/3 log base 2n approximation by Fagan Singh. Instead, the first asymptotic improvement on the log n factor was given by looking at the other approach. It's easy to find a spanning tree. So we would like to find a spanning tree and then obtain a Eulerian graph via what is called a circulation to fix the in and out degree of vertices. So this is very similar. This is like the Christophidis approach for asymmetric TSP, if you know Christophidis algorithm for symmetric TSP. So this was done by Asapur, Gomansmadi, Ovescaran, and Saberi in 2010 in a beautiful paper. And let me just describe quickly why the asymmetric case is very different from the symmetric case. So here I have an instance where blue edges are very cheap. They've cost 1, whereas red edges have a huge cost of m. So basically, if I select a minimum spanning tree, I will only select blue edges. Here's one minimum spanning tree. The only wrong edge vertices that are not Eulerian is this guy is out degree 1 and in degree 0. And here's in degree 1 and out degree 0. So I can fix that by adding that red edge and that blue edge. So it's a cheap one. I only use 1 red edge. On the other hand, if I select another mean cost spanning tree, for example, this one, where I have 4 edges going from left to right, then I would need 4 red edges to go from right to left. So it's very different from symmetric TSP, if you know the analysis of Christophidis algorithm, that not all spanning trees here can be corrected cheaply. So what they did in their paper was to introduce the concept of fin trees, and they show that this, if you select a spanning tree uniform at random from a maximum entropy distribution from the LP solution, then you get a log n of a log n approximation algorithm. And this comes from the upper tail of the Chernoff band. This was further improved for planar unbounded genographs to be a constant by Ovescaran and Saberi, and a deep paper by Anari and Ovescaran gave a polylog-log upper bound integral gap, also using and generalizing the famous resolution of the Cannon-Singer problem. So what we did was to propose a kind of a new approach that is more closely related to the Fiscal-Biati-Maffiali approach, but we maintain some connectivity in each step. Okay, so our new approach is to, I guess it's best described here. The previous approaches completely forgot about some of the constraints, so either only kept the Eulerian constraints or the connectivity constraints. In our new approach, we always maintain Eulerianicity, but we keep some of the connectivity requirements. The idea is, let's make each iteration a little bit harder, but by doing so, we will patch up the solution without paying too much. So we will ensure connectivity by not paying too much. And that led to the definition of what we call local connectivity ATSP, where we have input an edge-weighted digraph G, a partition of the vertices. And your goal is now to find a Eulerian multi-subset of edges such that each partition is crossed by a subtour. So here we have an example of a solution. You see that this partition is crossed by at least one subtour, and this partition here is crossed by two subtours. But each partition should be crossed by at least one of these subtours. So notice that this is easier question than ATSP, because in ATSP you have to find a tour that visits every vertex and then clearly also crosses each partition. Here we don't even require each vertex to be part of a cycle. You see in this solution, these two or these four vertices is not part of a cycle. There's a small fine print here that to get a good approximation, each subtour needs to be a good local approximation, but let me skip that detail. But maybe what is surprising is that we proved in 2015 that if you can solve this seemingly easier problem than ATSP, so if you can give a constant factor approximation for local connectivity ATSP, then that gives a constant factor approximation for ATSP. So in fact, they are equivalent up to constant factors, ATSP, and this with much smaller connectivity requirements. And we use that to give a constant factor for ATSP on special kind of matrix called node-weighted matrix. And then together with Jakub Tarnowski, who was previous a student of mine, and Laszlo Vég, who's a professor in LSE, we gave in 2017 a constant factor approximation for ATSP with respect to the standard LP relaxation. So this resolved at least that we could bound the strength of this relaxation up to constant factors, so it doesn't deteriorate as a function of the size of the instance. And the result is obtained by a sequence of reductions that adds more and more structure to the instance. And in the end, I will soon describe, in the end, the metrics look very structured. So then we could actually rely on the algorithmic technique that we developed in 2015. So let me now describe one key insight behind these reductions that also connects back to the techniques that we saw for the perfect matching problem. Okay, so what we're going to use is uncrossing plus duality to show that the general metrics that we have to consider when we look at this linear program are actually not that general. So recall that the Laminar family is a family of sets, is laminar if every two sets are either disjoint, like the green and the red, or one is a subset of the other, like the green and the light red. And I mentioned that this is a sparse set of constraints, small set of constraints in a laminar family. All right, so now if we look at an extreme point to our linear program relaxation for ATSP, we can see that actually an extreme point is defined by a laminar family of cut constraints. Okay, so I will only focus on the cut constraints here. So let me throw away the Eulerianicity constraints. So the extreme point to this linear program can be defined by a laminar family of these cut constraints. And also let me change this a little bit because the argument becomes a little easier. So let me take 2 minus epsilon, the size of S, where epsilon can be chosen to be arbitrarily small. If I do this, then any extreme point to this linear program is defined. If I look at the set of tight constraints, it must be a laminar family. So here I just changed it a little bit. Before it was 2 for every set, but let me take it 2 minus epsilon, the size of S where epsilon you can think of as small as you want going to 0. Then I claim that for any extreme point, the set of tight constraints forms a Laminar family. And let me prove this for you. I include one proof here. Okay, so suppose towards contradiction that there exist two sets A and B with a non-trivial intersection, and both of the sets are tight, meaning that the x value of the boundary of A is equal to 2 minus epsilon the size of A, and the x value of the boundary of B is equal to 2 minus epsilon the boundary of B. Okay, now one can by case analysis note that any edge is crossed at least as many times by the boundary of A and the boundary of B as the boundary of A minus B and B minus A. So this implies that the x value of the boundary of A plus the x value of the boundary of B is at least the x value of the boundary of A minus B plus the x value of the boundary of B minus A. Okay, you can do this by case distinguishing different types of edges. Okay, so we had that A and B were tight constraints, and A set minus B and B set minus A must be feasible constraints. So to combine this, we get that 2 minus epsilon the size of A plus 2 minus epsilon size of B is at least 2 minus epsilon A minus B plus 2 minus epsilon B minus A. But this is a contradiction because, you know, A plus B is bigger than A minus B plus B minus A. So this proves that if I take an extreme point to this linear program, then all the tight constraints must form a Laminar family. And now we use this to look at how general do the metrics we need to consider be when we do algorithms for ATSP with respect to this linear program. Okay, so in general instance, we have no structure on the edgeways. They can look arbitrarily bad. Now, if we do LP duality and uncrossing, we can actually show that we only need to look at instances where edge weights are defined by Laminar family of vertex subsets. Okay, and they have some value. So we have a Laminar family here of vertex subsets, and each set in our Laminar family has a weight. And if we have an edge in our graph, then the weight of this edge will just be the sum of weights of the subset of vertices that it crosses. So here it's 1 plus 4 is equal to 5. This edge will be 7 plus 5 plus 2. So that will be 14. And if there's an edge left in the other direction, notice that they will have the same weight because they cross the same sets. And this, you know, okay, so this is a very structured set of weight functions that we have to consider. And this gives us a recursive strategy that basically works like we contract the uppermost sets in our Laminar family. We solve as Tor by using, this is a node weighted metric, so we can use the result from 2015, and then we lift it back to a Tor in the original graph. So now when we lift it back, I didn't describe details, we might not visit all the vertices, but this will be dealt with like a recursive approach, almost like we did in the matching problem where we decompose into independent instances. So I left out the details here, but you have to trust me or ask me questions later on. I'm happy to answer them. Okay, so that gave us a constant factor approximation algorithm with respect to the standard LP. So since that result, quite some things have happened. So in particular, for the symmetric TSP, very recently, Carlin, Klein, and Oveskeran obtained this breakthrough results that they managed to improve the free-Hals approximation guarantee by Christofides. Actually, they use very similar algorithm that Christofides instead of select a random spanning tree, and the analysis is more complex, but the algorithm is very clean. Furthermore, Wygen and Traub managed to significantly simplify our approach and also get a much better guarantee. So now the guarantee for ATSP is 22. You know, these are good ratios, but they're still far from the conjecture right ratios with respect to the linear program, which is 4/3 for the symmetric case and 2 for asymmetric. So I would like to stress some open questions that I find fascinating here. So for the ATSP, it was very important that we kind of simplify the metrics that we worked on. And this allowed us to kind of use the result from 2015 to obtain general metrics. For symmetric TSP, we also have much better results when we have unweighted shortest path metrics, but we have somehow not been able to use the fact that we can look at these simplified weight functions yet in the symmetric case. I find that very interesting. Another question that relates to the thin spanning tree problem is whether we can solve the bottleneck ATSP problem. So that's to find a Hamiltonian cycle where we minimize the max weight edge instead of the sum of the edge weights. So this has been solved for, I think, 4 decades ago for symmetric TSP. The right answer is a 2 approximation, but for ATSP, it's still open whether one can obtain a constant factor approximation for bottleneck ATSP. The final thing I would like to say here is that so far everything I've talked about is with respect to the standard or held corp relaxation, but there's no reason to believe that this is the best relaxation or best algorithm that we can obtain. So maybe there are even better relaxations around the corner. It's time to take a step back and to summarize. So we consider the perfect matching problem and the traveling salesman problem. In both cases, we heavily relied on the Laminar structure of the phases and extreme points, and we also used kind of it that it decompose the problem in separate parts. Okay, so this allowed us to give deterministic parallel lines for general graphs, and I think for natural variance, the exact matching top K matching that I mentioned, we don't have a good polyhedral understanding, which prevents us from addressing these problems in the same manner. So currently, it's I think a beautiful open questions to get efficient deterministic arguments for these questions. And for ATSP, we allowed this uncrossing technique allowed us to look at very structured weight functions, and I think there was impressive recent progress, but we are far from having a tight understanding for this set of problems. Okay, so thank you very much for your attention.
All right, so thanks, Ulla, for an excellent presentation. If anyone has questions to Ulla, please ask them on the Discord server. Ulla will be happy to answer. All right, thanks, everyone. Have a good evening, good afternoon, or good morning.
Thank you.